Okay, so I think now we are complete. I hope so. So, okay, so let's start the afternoon session. It's my pleasure to introduce Gemma Krell. Please, Gemma.
Okay, great. Thanks very much for the introduction and the invitation to speak today. I'm sorry I can't be there in person. I had my PhD graduation a couple of weeks ago, so I had to kind of be here for that. But I hope the conference has been going well. I'm conscious of the fact as well that this, I think, when I looked at the schedule, this I think is the third last research talk. So after what I'm sure has been a productive and busy 2 weeks, but I don't know about all of you in the audience, but certainly my brain would be pretty fried by this point. So I'm hoping my talk will be a bit more of a survey talk, a bit more chill if you like, and hopefully just gives a bit of a flavour of some things I've been thinking about in the world of conjugacy growth, which I think is an area that, even if this is not familiar to you, it's a very open area. There's a lot of things we don't know and a lot of things yet to be explored that's worth looking into. So to start off with, I'm not going to talk about conjugacy at all. So you can forget about this word for a second. We're just going to focus on growth in groups for starters. So what I mean by counting things in groups, first of all. Hopefully, by the way, this is all clear, the screen and everything, but if anything's unclear or if anyone has questions, just someone yell at me. That's fine. Okay, so throughout this talk, G is always going to be a finitely generated group and X is going to be some finite generating set. So what do I mean by standard growth or kind of normal growth in G? Kind of informally, all I'm meaning is how many elements, how many group elements do I have of a certain length? So how many elements in G of length n, okay, that I want to count. The way we can define this, we can do this in two ways. We can define what's called a growth function and also a growth series. So the standard growth function, which I'll be denoting by little s here, more precisely is going to be the number of group elements in my group G which intersect a ball of radius n in the Cayley graph of my group with respect to this generating set. So you'll notice in my notation that I have kept this generating set X in the notation. We'll actually find later on that we don't need that, but for now the generating set is important. And indeed, you know, this definition involves a Cayley graph. As we know, we can have the same group in different generating sets, and obviously their Cayley graphs are different. So for the moment, we need to have this more precise definition of intersecting a ball of radius n in the Cayley graph. So that's our standard growth function. Obviously in the literature, a lot of the time this is just called the growth function because maybe people aren't interested in conjugacy, but we'll get to that later. So this is just normal counting group elements of length n. From that, we can then define a growth series, okay? And it's kind of just the most natural thing that you can do, which is just simply take this growth function and take the infinite generating series, okay? So we take our growth function and just add up like so, okay? And this is our standard growth series. Okay, so let's maybe do a quick example just to see how this works in practice or kind of what kind of things come up. So the example we're going to do is nice and easy. We're going to look at the free group on two generators, okay? So here we're just taking generators A and B. Here's my Cayley graph, the classic tree that we have. And we're first of all going to compute the standard growth function. So how many group elements do we have of length n? So this example is quite good in that for every word that I write over the generating set, that represents a unique element. Well, any geodesic word, I should say, represents a unique element, okay? So let's think about balls of radius n in this Cayley graph and how many elements we have. So starting from the very beginning, we clearly just have one element of length 0, as in the identity here in the middle, right? And that's all we have, okay? For length 1, we have 4 elements, right? Because we can go up to B, along to A, down to B inverse, and along to A inverse, right? And that gives us 4 elements here. So we have 4 elements of length 1, okay? Then kind of going beyond that, for example, when we have length 2, if we just take, say, this element A here on the right, we can't backtrack because that would give us AA inverse, which is the same as the identity, which is not of length 2, right? So from this point here, when I'm counting words of length 2, I'm going to have 3 options. I can either do AB, I could do AA, or AB inverse, and that's it, right? And you'll see in the other points as well, we also get 3 that we can choose from each point, right? Okay, so that gives us in total 12 group elements of length 2 altogether, okay? And so it's not too difficult to kind of show iteratively that this growth function is going to be 4 times 3 to the n minus 1 when n is greater than or equal to 1. Okay, and that's that. Okay, so that 3 is this idea that at every point that you're at, when we add a new letter, we can't backtrack. So we've only got 3 options at every stage. So this is clearly an exponential function, right, that we have. What about the growth series of this group with respect to this generating set? So just taking from the definition, so we have one group element, namely the identity of length 0, and then we're summing up from greater than or equal to 1 of this function 4 times 3 to the n minus 1 of z to the n, okay? So then from here we can just do a little bit of kind of tricks, if you like, to make this look nicer. So I can take 4/3 out and I'll get instead a geometric series, which I can then rewrite like this. This is all subject to me actually working this out properly, which hopefully I have. So we get this geometric series, and yeah, with a bit of simplifying, we end up with the following result, okay? So this gives us what we call, which I'll define properly later on, this gives us a rational growth series. So rational being that I can write this as a fraction of polynomials. Okay, so that's standard growth, but you might be wondering, why are we doing all of this? What's the motivation behind studying counting things in groups? This is like a very well studied area of group theory, and there's tons of results about growths of groups, tons of textbooks about it as well. I'd say kind of 2 of the main things just to highlight that people have focused on is, first of all, what types of growth functions and growth series can you have? So again, I'm being a bit vague here. We'll define all of this better in a little bit. So yeah, can we have polynomial growth? Can we have intermediate growth, for example? Was a big open question for a while. That sort of thing. Another area of interest is studying growth of groups and understanding what that implies in terms of properties of the group. Okay, so essentially finding links between growth of groups and group properties. Okay, so for example, there's a really nice theorem of Gromov, where it was shown that groups have polynomial growth if and only if they are virtually nilpotent. So we have, a complete characterization of which groups will have, say, polynomial growth, which is quite cool. So what I want to do today, obviously my title of my talk was not just growth of groups. What I want to do today is ask the question, well, what happens when we start counting conjugacy classes rather than just group elements? And what's the story there, what's going on, what kind of results we can have. Okay, so that's going to be now kind of more the focus of my talk. So what do I mean by conjugacy growth now? Well, funnily enough, it is essentially the same as normal growth, but now instead of counting group elements, I'm just going to count conjugacy classes, okay? So same as before, I'm still talking about finitely generated groups with a generating set X. And so now we're going to define my conjugacy growth function to be the number of conjugacy classes of length n. Okay, so you might be thinking, okay, what exactly do I mean by that? What I mean is, you know, in our conjugacy class, we have lots of group elements that lie in that conjugacy class. But out of all those group elements that are, say, geodesic, we have geodesic representatives for, what's the minimal length of a representative in that class, okay? This will become a bit clearer when I do an example. So this is our conjugacy growth function, like so. And again, we can do similar to before, we can construct an infinite generating series out of this function, same as before, and that gives us our conjugacy growth series, like so. So really there's nothing different here to before, we're just now thinking conjugacy classes instead of group elements, and so that's fine. All right, so we're now going to do another example. It's not going to be the free group, but yeah, it's kind of a more interesting group if you like. The group we're going to look at is the infinite dihedral group, which can be presented as follows. If you've not seen this group before, think of your finite dihedral group. So that's a polygon that is, say, generated by two reflections. Imagine taking that polygon and kind of expanding it out to the real line. That is essentially what this group is, okay? And what this group is also equivalent to is the free product of two cyclic groups of order 2, okay? So what's going on in this group, or in particular, what's happening with conjugacy classes, okay? So let's maybe get a bit of notation and kind of a handle on what's going on, okay? So our generating set here is AB, and I'm going to let X be just this A and B to plus or minus 1, just to make things a bit clearer. And I'm going to let X star denote all words over X, okay? So first of all, you'll notice that each generator has order 2, right? So A inverse is the same as A, B inverse is the same as B, okay? So what that means is if I have a word over this generating set that is geodesic, that's representing a group element, I can write it as some sort of alternating A's and B's. So it might look something like A, B, A, da 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 da, A, B, like that, okay? It might start with B, it might end with B, we don't know, but any pairs of A squares, B squares, we can cancel, okay? And that, you know, this matches up with how you know free products work already, okay? There's nothing kind of new about that. What I guess maybe is new, and I leave kind of as an exercise, but this also just kind of comes from how free products work, is if you give me two words, say U and V, over this generating set, and we'll assume they're geodesic in the sense that any of these squareds we're getting rid of, right? Then U and V are conjugate to each other, so this is what I mean by conjugate. If and only if U and V are related to each other only by a cyclic permutation. Okay, so that's not too tricky to show. So obviously cyclically permuting words is going to preserve conjugacy, but then your question might be, is there anything else that you can do to somehow get from one conjugate element to the other? But what we're saying here is no, that can't happen, that you just need to do cyclic permutations, and that's it. So what that means is actually counting conjugacy classes in this group is somewhat straightforward to do. So here we're going to do a few cases. So here's our group and a bunch of lengths. I've skipped length 0 because again we just have one element, which is the identity, and that's fine. So let's first just count group elements. So what do we have of length 1? We have A and we have B, and that's it, right? They clearly can't be conjugate to each other because they're not cyclic permutations of each other, okay? And so that gives us 2 conjugacy classes of length 1. Okay, what about words of length 2? Well, we could have the word AB and we could have the word BA. And that's it in terms of geodesic words, right? Because we can't have any squares, okay? But AB and BA are just a cyclic permutation of each other. So these guys are actually conjugate to each other. And so we really only have one conjugacy class. We've got 2 group elements of length 2. We've only got one conjugacy class of length 2. Okay, what about length 3? Length 3, we have the word ABA and we have the word BAB, okay? They're clearly not a cyclic permutation of each other. And what's worse is if we were to take a cyclic permutation, we actually get to a smaller group element. So for example, if I take the word ABA, I can cyclically permute the A round, and that gets me A squared B, but we know A squared is just equal to 1, so this is really just equal to B, right? So this is really conjugate to B, and BAB is conjugate to A, and so actually we don't have any conjugacy classes of length 3 because really they are conjugate to something of length 1, okay, and we've already counted those already. Okay, length 4, these will do a little bit quicker. You get the same idea. So these guys, we only have 2 group elements. They are conjugate to each other because they're cyclic permutations. And so, oh sorry, that gives you 1 element, not 2. And then similarly for length 5, again, you have the same problem that these elements are actually conjugate to an element of shorter length, and so we have 0. And so what you'll find is actually everything of odd length, we don't need to count anything from that. All right, so what is our conjugacy growth function and series out of this? So I skipped length 0, so we'll do the function first of all. I skipped length 0, but we just have 1 as in the identity. We have 2 elements of length 1, and then beyond that, so when n is greater than or equal to 2, we'll either have 1 conjugacy class when our n is even, or we'll have none when our n is odd, okay, just by essentially applying this pattern again and again. And that's our conjugacy growth function for the infinite dihedral group. What about the series? Well, the series this time we're going to have, again, we have 1 element of length 0, we have 2 of length 1, and then we are just taking essentially the even power. So we'll get, oh, look at that, z squared, z to the 4, so on and so on, okay? And again, a little bit of just kind of working with geometric series here. So I can write this like this. And then I can apply, we can rewrite this like so. And so we end up with this function here. Like so, okay. And so again, we've got something that is a rational series out of that. All right, cool. So that's kind of the main definitions that we need for today. In some ways, though, I have kind of cheated a little bit in that I mentioned things like exponential growth, polynomial growth, but I didn't really tell you what I meant by that. And so we need to kind of clarify definitions a little bit and create a notion of equivalent functions. So that's what we're going to do next. Again, this isn't so much related to conjugacy, but this will be helpful later on. Okay, so first of all, we want to have a notion of equivalent functions. This definition, I'd say, comes in like different forms, so you've maybe seen this in a slightly different way. It's probably come up in the last 2 weeks in this conference. But say we have two functions like so. I'm going to first define what I call one function dominating the other, which I'm going to write like this. If there exists some constant such that this function, my f, is bounded above like so. Like that, okay? And this is for all x in n. Okay, so you may have seen this slightly differently. So that's saying that, like, say G dominates F, and if we have that they both dominate each other, so in the sense that we have this way around and the other way around, then we say that F and G are equivalent. Okay, and somewhat confusingly, which I apologize, often the notation for this is also this squiggly line that we use for conjugacy, but that's often what we mean by equivalent functions. Okay, so for example, you can have two functions which are, say, both polynomial but slightly different polynomials. We'll now just say they are a polynomial in the class of polynomial functions. Okay. Now, why is that relevant to us? Well, so far when I've been doing these definitions of both standard growth and the conjugacy growth function, I've been defining the generating set. And in a way that made sense. That was important because we're essentially looking at balls in the Cayley graph, right? But as it turns out, if you give me two different generating sets for the same group, actually we don't need to worry too much when it comes to functions, okay? And in particular, the standard growth function will be equivalent to, in one generating set, will be equivalent to the standard growth function in the other generating set. And similarly for conjugacy growth, we get the same thing, okay? So that's not too difficult an exercise to show, all right? So now when I talk about groups having polynomial growth, groups having exponential growth, right? If I take generating sets, the exact growth functions may be slightly different, but they will still have the same kind of form, if you like, up to this equivalence. Good, okay, so that's growth functions. What I've kind of been working on actually is more been focusing on the growth series. So this infinite generating series that you take from the function and trying to understand what does this series look like, okay? So this has got nothing to do with growth at all. This is just kind of understanding types of series. This is by no means the full list of options that you have, but these are the ones I'm going to focus on for today. So we have some sort of formal power series. We've seen rational already, but just to give the formal definition. But it basically says that you can write my series as some sort of fraction of polynomials, right? So for some P and Q, like so. Okay, and that's that. So in a sense, rational is like nice. You know, we can write it in a nice way. Then it starts to go a bit more downhill. So we say a series is algebraic if my series f of z is a solution to a polynomial equation with coefficients in QZ. Okay. And then transcendental, in some ways is the easiest definition, is just simply that the series is not algebraic. Okay, so if you're familiar with algebraic and transcendental numbers, that's kind of the idea here. Okay, so transcendental essentially is very bad, a very messy series that we have. Fine. Now we can get on to kind of the more proper research, or kind of the more new stuff that's been going on. So I'm interested in understanding conjugacy growth, and in particular the conjugacy growth series. And part of the motivation for this comes from quite a strong conjecture that these people will not mind me saying is still somewhat, this conjecture might change basically, okay? They're not sure if maybe we need to add more conditions to this. And what the conjecture basically says is that the conjugacy growth series for most groups is quite bad, okay? So more formally, what I mean by that is that the conjugacy growth series of finitely presented groups which are not virtually abelian, so virtually abelian being a group with a finite index subgroup that is abelian. So these virtually abelian groups we're treating as like nice groups. So apart from these, they have transcendental conjugacy growth series. Okay, so let me just mention a couple of caveats to this and why, like I say, this may change. You know, it's a very recent conjecture, and it really is wide open at the minute. So I mentioned a while back, we have this notion of equivalent functions, and we don't need to worry about generating sets when it comes to growth functions for both standard growth and conjugacy growth functions. The same cannot be said for series. Okay, it gets a lot more complicated with generating sets. Okay. So for example, one very weird thing that's going on in conjugacy classes is we don't know what happens when we say take finite index subgroups. So there's an example from Hull and Olsen from 2013 where they constructed a kind of a weird example of two groups. One is of index 2 in the other. This group H over here has two conjugacy classes, and that's it, right? But G over here, the conjugacy growth function is actually exponential. So very different, right? Now, with this example, what I will say is this was a not finitely presented group, G, that they constructed. So that's why this finitely presented is in here, okay, to basically kind of rule out this kind of weird case that we have. And yes, as I mentioned, what's kind of open is what happens with different generating sets to the series, okay? So one thing I'll mention is if we look at the standard growth series of groups, changing generating sets can be problematic. Okay, so we do have to consider generating sets. And for standard growth, this comes from Stoll in '96. Basically, he was looking at the Heisenberg group, and with different generating sets, he could either get rational growth series or transcendental growth series, depending on what generating set you're focusing on. So for that, we just don't know. And for conjugacy growth, we have no idea. So the results we have are either with respect to all generating sets or with respect to, say, one generating set in a particular group. But we really don't know what happens when we don't have a similar kind of example yet for conjugacy growth that's like Stoll, that when we change generating sets, we do get something wildly different. But that's mainly because we just don't know a lot of things about conjugacy growth. But that's all sounding quite pessimistic. So let me say what we do know about conjugacy growth, because there has been a lot of research in this recently. So let me first give a list of groups we know that support this conjecture that the conjugacy growth series of groups most of the time is transcendental. I'm going to focus first of all on ones for all generating sets. One thing with this conjecture is, well, it has this part here that we're excluding virtually abelian groups. Okay, so it'd be good to know what do virtually abelian groups look like. And this was done by kind of my academic sibling, if you like, Alex Evitz. He showed that virtually abelian groups have rational conjugacy growth for any generating sets. So that's good. So that says, right, virtually abelian are nice, and we can deal with them. And then everything else we have so far that we know is transcendental that matches the conjecture. So for example, hyperbolic groups, these have transcendental conjugacy growth so long as my group is not virtually cyclic, okay? And that's basically, because if it's virtually cyclic, we've then got virtually abelian and we're good, okay? And this result was something called Riven's conjecture that was open for a long time and was, there was kind of two main papers that proved one direction and then the other, using a lot of geometry and formal language theory to prove this. So it was a lot of work went into this, basically. So here's kind of several names. Make sure to spell everyone right. Rees in a couple of papers in 2016, 2017. More recently, but keeping on the geometric side, we also know for relatively hyperbolic groups, this is also transcendental. This was by Geikman and Yang. And again, this was quite geometric arguments. They used something called contracting elements in groups to understand conjugacy growth. And then everything else that we know so far is based on, say, one type of generating set. Okay, so this is kind of everything we know for all generating sets so far. So here's one I did earlier. So for example, we know for soluble Bohm-Sachs-Zollitar groups, again, these are transcendental. So all of these next results are with respect to some generating set. It's often called the standard generating set, but we just fixed the generating set and said that's that. So this was by Chibano, Evitz, and Ho in that same paper where the conjugacy conjecture is. We also know it for right-angled Artin and Coxeter groups. This essentially comes from the Geikman-Yang paper as well. One thing I did in my PhD and soon to be on the archive is extended this to some virtual RAGs and right-angled Coxeter groups. This is a difficulty when your supervisor has the same last name starting with the same letters. You're both C's. But yeah, so this is 24, maybe 25 on the archive, depending on if I get it done before Christmas. And then lastly, some Reith products. We also have some transcendental results as well. Right, okay, so this is everything we know at this point. So before I get to kind of more recent results that I've done with my supervisor, I just want to highlight kind of some of the behavior that's going on, or kind of the typical behavior that's leading to all these results and where we think this is maybe kind of going next. So this is in a sense my little toolkit on conjugacy growth on some of the ideas that have been used so far, okay? So first of all, we have formal languages have been playing a key part in all of this. So for example, you can create a formal language that has, say, a representative for every single conjugacy class. And then you can look at, is this language regular? Is it context-free, etc., etc. And then from that, maybe you can determine something about the conjugacy growth series, right? Or even the conjugacy growth function. So that's kind of one direction that people have looked at, I've looked at as well. There's also a lot of geometry involved in all of this. So for example, for hyperbolic groups, proving transcendental conjugacy growth, a lot of that work came from looking at thin triangles in hyperbolic space and what we know about conjugacy in hyperbolic groups. So a lot of that was very important. But what I kind of want to flag as kind of a key thing that's coming up time and time again is some asymptotics that are proving quite helpful for trying to prove groups have transcendental conjugacy growth, which support this conjecture. So we have a really nice result of flagellae, which is nothing to do with growth of groups or conjugacy growth. It's just to do with growth functions. And what it says is, suppose you have just some growth function, as in like, you know, counting things of length n sort of thing, for example. And so we have a growth function, little g, and we have the growth series, which again, same as before, we're just taking the generating series of this function, right? Nothing kind of weird there. What the main part of the theorem says is if my function looks a certain way, I can determine that the series is going to be transcendental. So, more precisely, if we have some constants, a, b, and rho, such that we have the following inequality, like so. So it's bounded above and below up to these constants a and b by this rho to the n over n. Okay. If this is true, then we know that my series has to be transcendental. Okay. So this is really helpful for us in that in trying to understand the conjugacy growth series, we can just look at the conjugacy growth function and see if we can get these bounds, and then we're done. Very much simplifying things there, but that's kind of the gist of what's been happening recently. And in fact, what is coming up time and time again, and what we think is probably true, well, okay, that's maybe too big a conjecture, but what we think might be true is that if you give me any group that say has exponential standard growth, okay, so we'll call this Sn, then what we're finding is that the conjugacy growth tends to be something like the standard growth divided by n, okay? And in fact, what's kind of more happening more often, and I'm putting this as inverted commas because I'm kind of waving my hands a little bit, is that things are conjugate if and only if they are equal up to a cyclic permutation only. And that's the only way you can get between conjugate elements. And whenever you have that kind of behavior, that's really nice for using this flageolet because counting equivalent words up to cyclic permutations is easy. You just count the number of words you have of length n and then divide by n because that's taking into account all these cycles. And so we then tend to get this transcendental behavior. So yeah, I think I've got time to just go back to the free group that we had way at the beginning, right? When we were counting group elements. Free groups are actually also, well, it's not straightforward to work out conjugacy. It's a lot of work put into it. But to understand conjugacy is fairly straightforward in that we essentially need to look at what's called cyclically reduced words. Okay, so these are all words that don't look something like V inverse WV, okay? And the reason being, in the free group, I could take a cyclic permutation and then I could cancel it, okay? And in the free group, if you give me two words, say U and V, that are cyclically reduced, we precisely have this behavior, a bit like in the infinite dihedral group as well, that two things are conjugate if and only if we can only get between them via cyclic permutations, okay? So in trying to determine the conjugacy growth function, essentially, and again, I'm being very vague in this is not a proper proof, it is roughly speaking the number of cyclically reduced words of length n divided by n at any point, right? Because the cyclically reduced words are all our minimal representatives for each conjugacy class. They are equal up to a cyclic permutation, so we need to divide by n. And in free groups, this is roughly something like 2d minus 1 to the n over n, which you'll notice is this d is fixed based on, say, the rank of my free group. And this is very much matching the inequalities we have here in the flageolet, right? And so what we can say is actually, and actually I should have had x here, the conjugacy growth series is going to be transcendental. Which makes sense because free groups are hyperbolic and that should match up anyway. But that's kind of a more direct way of proving, say, free groups have transcendental growth. Okay, so I think I have a few minutes left, so I can mention just a little bit about some stuff I've worked on, and just finish off with where this is all going next. So the groups I've been looking at are something called dihedral-Artin groups. So if you've seen Artin groups, this falls into that class. And this is precisely the Artin groups that are generated by two elements, okay? So we have two generators A and B, and they have this type of braid relation of length m, like so, like that, okay? So myself and my supervisor, we wanted to see, do we get transcendental conjugacy growth in these groups? But let me just mention maybe some known examples. If we take the two extremes of this group, as in when m is 2 or when m is infinity, this group here is just a free abelian group because our relation becomes AB equals BA, and that we know has rational conjugacy growth. So, okay, our statement now becomes, what's the conjugacy growth for m at least 3, right? The other extreme, when it's infinity or you have no relation, we have the free group again on two generators. And as we've just seen, that has transcendental conjugacy growth. So in a way, we already know those. But everything in between, we didn't know what was going on. And so our result says that these do have transcendental conjugacy growth. So our conjecture still is still open, but is still valid. Dihedral-Artin groups is transcendental. Unfortunately, our results that we have are with respect to one generating set. Okay, so this is with respect to some generating set. We honestly don't know for other generating sets what's going on. I really don't have the answer to that. Who knows? Basically, that's maybe another thing to be looking at. We basically chose a generating set that made looking at counting group elements really nice. And then we found that we had this kind of similar behavior of counting conjugacy classes was essentially up to cyclic permutation with some funky stuff going on in the background that we had to be a bit careful about counting. But I'm going to basically sweep that under the rug and say that was how we got transcendental using the flageolet result that I mentioned before. So to finish things off, what next, basically? So hopefully you'll all kind of see that this area has like lots of potential, right? There's loads of groups we don't know what's going on, basically, and it would be good to have more examples. In particular, I'd say one of the main things we really don't know is what happens when we take different generating sets. So like I was saying, the result I have with my old supervisor, we don't know what happens with different generating sets. We'd need some new tools to understand that. Another thing that keeps coming up again and again, that we think is maybe true, but we're not sure, is groups which are central extensions of hyperbolic groups. These tend to always have transcendental conjugacy growth. So these are groups where, actually, why am I writing like that? There we go. We have some sort of short exact sequence where this group here is a hyperbolic group, and we're maybe interested in this group G in the middle. What is its conjugacy growth? So dihedral-Artin groups are examples of central extensions of hyperbolic groups. And so we think maybe there's some, we can maybe prove conjugacy growth for a bigger class of groups. We don't know. And then lastly, what about other Artin groups? We don't know what's going on. What I will say is there's a nice result of Heitel. I now forget what year. I think it's maybe 17, something like that. But he showed that extra large type, these have transcendental conjugacy growth. So what I would say is, if you're thinking about this, don't look at extra large type. Look at something between dihedral and extra large type. That's what would be interesting to look at next. But I think otherwise that's everything I wanted to say. So thanks very much.
Thanks, Gemma. Are there any questions from the audience? One more.
Hi. You mentioned this examples of Michael Stoll from 1996 about the kind of ordinary word growth. So have you looked at the conjugacy kind of growth in these groups with respect to the generating sets that he provided? I mean, these kind of surprising ones where you do get rational things.
So I haven't personally, mainly because I know so little about Heisenberg groups. But it is, yes, it's people are looking at conjugacy growth in Heisenberg groups. I'm not sure so much people have actually looked directly at, like you say, the two different generating sets and whether you get a similar result. But I think that's partly because we are still just trying to understand conjugacy in Heisenberg groups to begin with. So yes, that still, yeah, would be worth looking at.
Thank you.
Yes, thanks for the talk. I wonder about two things. So the first is, if I understand your method right in proving transcendental things, you always have to start with a group with exponential growth. And so somehow your methods cannot prove transcendence of the conjugacy growth theories for nilpotent group, say.
Again, we're not sure. Yeah. So yeah, I guess for nilpotent groups, yeah, we might have to come up with some new methods perhaps. But that's also open. And again, I know of people who are working on nilpotent groups, and that's still to be determined.
So now you have a lot of groups with transcendental conjugacy growth theories. In transcendental number theory, there's the notion of transcendence measures. So you can somehow say that some numbers are more transcendent than others. Is there something comparable in for these series? So is the growth theories of hyperbolic groups worse than that of, I don't know, Artin groups?
That's a great question. I have not heard of this before, I'll be honest. I don't know, in all honesty. Yeah, which are kind of worse than others. Yeah, that might be something worth looking into. Yeah.
Thanks.
You hear me? Yeah. So I was going to ask a similar question. So among transcendental functions, there are like classes like definite functions and so on. So maybe the examples that we have, do we see that the functions, the generating series we get are definite or something like that, maybe?
Yeah, so definite I hadn't mentioned in kind of my list of definitions. As far as I know, we don't have any results of definite in terms of conjugacy growth. But again, I know people who are working on it. So yes, that may well be a possibility as well.
Thank you.
If I might make a small addition, the Heisenberg growth, the standard Heisenberg group has conjugacy growth something n squared ln, if I remember correctly, which is kind of in between two polynomial growths. And if I'm not mistaken, this excludes it from being rational. So I guess this kind of answers two questions here.
Cool.
And this is shown by Alex, if I'm not mistaken, Alex Havitz.
Are there more questions? No, so let's thank Gemma again. We have, well, a tea break, I guess. And, well, don't forget that the posters are there. So if you haven't seen all of them, maybe that's a chance for you to read. Maybe you have one more today. Thanks, Gemma.
Thanks for having me.